with the next presentation, Lucas Torrealba, who is a researcher in NIC Chile Research Labs, and he's in charge of the project on malicious domain detection. And his presentation is using AI in DNS analysis, detecting randomly generated domains. Hi, good everyone. I'm going to speak about using AI in DNS analysis and particularly detecting randomly generated domains. This is a collaborative work done with different entities. Pedro Cáceres from AIT, Austrian Institute of Technology, Javier Bustes and Ivana Bachmann, who were my professors of my PhD paper from NIC Chile, Ms. Lack-Findrich, and from Science Security Group, and Herman Capdegurat from the University Republic and the Ceval Plan in Uruguay. Before speaking about this topic, I would like to first explain what these domains are. These are algorithm-generated domains. You deliver an algorithm at a starting point or a seed. If two machines have the same algorithm and the same starting point, they generate the same domains. We detect two families, the algorithmically defined algorithms. These are random. This is something that is impossible to pronounce. And then we have the dictionary-based domains, which is a combination of words. It could be words and something that is also done randomly. We are aware what they know. Now, the question is, why is it important to detect these? We have three main reasons. One is botnet control. The other is malware mitigation. We have seen that these domains have been used to propagate malware and particularly to prevent phishing. We have realized that in recent years, these domains have been frequently used to host phishing sites. And regarding botnet control, I didn't explain this very much. I like to give an example. Here we have an attacker that communicates with its server, command and control. So previously, he had infected a network of devices or computers. So this attacker always wishes to maintain communication with its network to carry out different types of attacks. For example, DDoS. How do they go about this? That is why we have DNS. So machines do a DNS query for a domain. What domain? The one that generates the algorithm. So in this case, the attacker only registers one domain name, and with that, the attacker can carry out the communication. What happens afterwards? Well, the domain crashes, or it is included in a blacklist, the domain and the IP. So what does the attacker do? It registers another domain, and with that, it maintains communication with the network. So we already saw what this is and why it is important to detect these. But before explaining the models we use, let me explain the data sets. This is a public data set which is balanced. It contains 50% of benign domains obtained through Alexa. Alexa is not used anymore, but we have another list which is the Cisco Talos list. And then the other 50% of the data correspond to 25 DGA families. 21 families are randomly, and 4 are based on dictionaries. Let me now explain the implemented models. The first approach, to tell the truth, we didn't wish to use AI. We wanted to understand how these domains work. So we based ourselves on a paper by Chow, who basically to each domain name values associated. So if this value is high, the domain is legible. If it is low, the domain will be illegible. We identified two phases. One is the creation of a dictionary, and the other is the domain prediction. This example is the creation of the dictionary. I only did this with trigrams. This is a popular domain name list. These are benign and were not generated algorithmically. We divided this domain in trigrams. NIC Labs is divided into NIC, Lab, and CI5. Then we check the occurrence of these trigrams in my data set. Here Nick had 238 occurrences. And then a logarithmic function was applied whereby we have a dictionary that has trigrams, and this is repeated for 3, 4, 5, and 7 grams. Now, what is a prediction? This is the important part. How was this done? Originally, you have a domain name, and once again, this was segmented in the n grams. This is only 3 grams. So we go to the dictionary that we already created and we add up the weights. Here the addition is 17.33. When we combine this with the values of 4, 5, 6, and 7 grams, we have a value of 36.18. We identified something here. If my domain grows, and continues to grow, the likelihood is only to increase. I can never decrease. So what did we do now? We included a reductor. So this was based on the domain length. So the original value of 17.33 in the n grams was reduced to 3.06. Therefore, the reputation value also decreased. As we said that the first thing we do, here we lost the audio. So this was then compared. There are many graphs here. We have 25 graphs. I don't want you to read all of them, but I want you to note that our model in these 25 cases exceeds the original algorithm. There's a larger area above the curve, and because this is a self-balanced set and it's a binary combination, it's a better predictor.
However, there are 4 families that are marked, and although we changed it in the original, now here it is almost random. Which of those families? They are dictionary based, and it makes sense because this algorithm focuses on seeing the algorithms that are almost legible. And this is cumulative, and you see that most lines are very close to 0 in the reputation value, but there are 5 lines that are not. Which are those 5? Alexa, benign domains, and the other 4 families that are dictionary based. So that's what we did. Then we had to use AI. We wanted to start with a machine learning model just using 3 characteristics: the reputation value that we already calculated, the domain length, and the Shannon entropy. And so we use this random forest. Here we see the distributions, and we see that our reputation value, the 4 families that are in red, is very high. So here we can see that our algorithm with just 3 characteristics behaves better. And there over the curve, well, we see the false positives against false negatives, and we see that it's a better predictor. Even so, there was still a long way to run because we realized that we couldn't detect the dictionary-based domains. So this is the DOM2-VEC model. This is the general overview of DOM2-VEC, separating a domain name, and I'm going to explain it case by case. So how do you separate? It's quite standard. We take words, we arrange them by frequency, we match them with a probability, then we give them a domain, and we divide them by probability. It's usually what you do to measure the time down. And then, so before I explain this model, DOM2-VEC, let me see, a word2VEC is a natural language processing technique where we use neural networks to map words or tokens, and in this case, domains. And it generates embeddings that capture semantics similarities. I like to explain this with an example. Here we have our new space. In this case, we have France. If we add a vector, we can reach Paris. And if we are in Italy, if we add the same vector, we should reach Rome. That's the good thing about word2VEC. The bad thing is that words mean something. For instance, in Spanish, banco is a place either like is a bench or a bank where you can draw money. So This model has two main architectures. On the one hand, SIBO, and on the other, skipgram. And I'd like to show it with an example. Here I have a phrase that says the DNS resolves domain names to IP addresses with a window size of 2. I have 2 words to the left and 2 to the right, and we have our target word domain. So the context is what is to the left and to the right. What does SIBO do? It takes the context and gives you the target word. And skipgram tries to predict the context. What do we want? We try to predict context because it may be the case that we put together 2 words and the context may be completely different. So that's strange. That is why we use the skipgram architecture. The length of the vector is 100 and the size of the window is 5. That's quite standard. So we trained this model using Wikipedia text, the corpus. So finally, for each word that we had separated, we run it through our DOM2Vec, a word2vec, and we have vector representations. And we are going to have more than one. What do? We group them somehow, in this case in 5 different ways. And therefore, as we have 5 different ways of doing it, and each way is the 100 vector, overall we have 500 new characteristics. And with this, once again, we train a machine learning model, a random forest, where we took the 2 previous features and we add the 500 new characteristics that were drawn from word2vec. Here, there are a couple of results. Here we did a multi-dimensional, basically this is for a space of 500 dimensions in just 2 dimensions, and we can see that the domains of Alexa that are not randomly generated release much more compressed space. So we would be able to detect them. And again, as we like graphs, we also see that our new model, the DOM2Vec, has a higher area under the curve, so it has a better yield. And specifically, when we look at close to 0 in the false positive, the true positives are high. And this is of interest in this case because we don't want to mispredict, so that is to harm benign domains. So finally, we build the deep DOM2Vec. Basically, it's the same architecture but with a different classifier. In this case, we occupy a convolutional neuronal network with 5 layers, with 1 dimension, with ReLU activation, with batch normalization. And once again, let's see the results. Here we see all the models that I mentioned previously. On the one hand, the first 2 models are these where we are not using AI at all. We only calculate this reputation value. Then in green, we see with what we did. So here we have the models that use DOM2Vec, but we use round forest, all these that you have here, anagram, etc. So we saw this with convolutional networks with 5 layers, and we see that we have both a recall of performance of 97%. And again, we go back to this chart. Here we can see in the black line that D2V have very good yield. Specifically in your right chart, where you see the false positives from 0 to 10, we see that our models predict, because true positives have a very high probability. So it's good to predict. So what do we conclude? First of all, we introduce the DOM2-VEC model with an innovative approach where we can map the domain names in a latent space, high dimension, and it is very promising, at least in this set of data. In addition to that, the models that we built with DOM2-VEC can successfully predict with a very low false positive rate. And this is absolutely necessary for cybersecurity. That is, not to harm the benign domains. And Word2Vec shows very good results when the idea is to use the dictionary-based domains versus those that are randomly generated. Now, so what's in the pipeline and what's for the future? Well, we are conducting a benchmark with different models so as to be able to compare. What is the idea? The idea is that this tool would be open for all, for the academia, the industry, the community, everybody. So that tomorrow, when hopefully you'll be able to face algorithmically generated you can use it, and you can replicate this in different scenarios, because in our case our set of data was balanced, but in real life we don't have a net balance of the algorithmically generated domains and those that are not. So we are testing this in different scenarios, and we are using all these models when we for instance, what happens when you have families that you didn't know for training? And finally, we are comparing the dictionary-based families versus the randomly generated families. So in the future, we wanted to explore AI techniques that can be applied to better interpret the models to estimate CNN and LSTM, because random forest models, I can see what are the best characteristics, but in a deeper model, sometimes it's seen as a black box unless we can use the explainable AI. Here you have references. The presentation is online, just in case you want to see it. Here we have all the papers so far. They have to do with I just presented, and if you have any doubts, any comments, whatever, you can reach me. That's my email. So we can get together over a cup of coffee. Thank you. If you have any questions for Lucas, we have time for a couple of questions. Hello, Lucas. Hugo Salgado here. How do you imagine that this can get integrated in the real-life internet? That is, once you generate a code, would this make it possible for a registry to block, for instance, people that are trying to enter a domain, or companies that sell traffic? Well, I work at NIC Chile at the lab. NIC has the CTLD of the register.cl. Now, if it's an algorithm that was generated, or a domain that was generated through an algorithm, doesn't mean that it is to mistrust it, because if you have just the name with the domain, you can't tell whether they're benign or not. So it's very important to understand the context of the domain names before you discard them or you block them. Thank you. Any other questions? Thank you, Lucas.